Hello and welcome to Living Proof, the joint podcast between plus.maths.org and the Isaac Newton Institute for Mathematical Sciences. I'm Marianne Freiberger.
And I'm Rachel Thomas. Marianne, do you remember back in 2019 when we spoke to Steven Niederer about digital twins?
Oh yeah, I remember that. That was really interesting because for once we got to leave the offices of the Center for Mathematical Sciences and we went into a hospital to interview Steven. Steven told us about this idea of having a mathematical description of your entire body, which could help you and your doctors make decisions about your health and your medical care. Now, you got to speak to Steven again, didn't you?
That's right. Steven's now chair in biomedical engineering at Imperial College London. And I also spoke to his colleague, Richard Wilkinson, who's professor of statistics at the University of Nottingham. And when we spoke to Steven back in 2019, he just helped organise a programme at the Isaac Newton Institute called the Fickle Heart, which was focused on one particular part of a digital twin, a mathematical model of a human heart.
Yeah, and these models, they're just mathematical descriptions. So they use equations to describe the physics of what's going on in the heart. So these are things like the fluid flow and the electrical waves that move across the heart as it pumps. And these kind of processes, they can be described using something called differential equations. Now, normally you'd fit these differential equations together, and then in this linked up way, that would give you this mathematical description of a heart. But as we'll hear in this podcast, these digital hearts, they now also bring in machine learning to make sense of a lot of the data that has been gathered. So data has been gathered from individual patients so that the mathematical model of their heart can be personalized to exactly fit them. But then if you take all this data gathered from many patients together and link it up, then you get a wealth of data that you can use machine learning on. And machine learning, of course, is very good at spotting patterns in data and mining data for information that otherwise wouldn't be so easy to see. Now, you got to speak to Steven again because of another program at the Newton Institute that happened in the summer called Representing, Calibrating and Leveraging Prediction Uncertainty from Statistics to Machine Learning.
That's right. And that program is co-organized by Richard, and it's a mouthful, so let's call it the RCL program. And it might not sound like it has much to do with digital twins, but as we'll hear in the podcast, all of these three aspects, representation, calibration, and leveraging, are really important factors in building digital twins. And we'll hear from Richard how the work done in that initial Fickle Heart program fed into this year's RCL program. And Steven would tell us about this huge project he's now leading called CVDNet that's making the digital hearts originally discussed back in 2019 in the Fickle Heart program, it's making them a reality today. But first of all, I asked Steven to remind us, what is a digital twin?
So in our context, and I appreciate that there are many contexts, we would say that a digital twin is a computational model or in silico representation of a particular asset or entity. And in this case, we're thinking about the heart or the cardiovascular system that is based on a specific individual and that is going to be updated with information through time from sensors or repeat measurements. And that will then inform decisions that add value, I believe is the formal definition. And in our context, that might be giving you better diagnostics to explain, is the heart stiffer? Is it activating well? Is it pumping blood well? It might be making forecasts to say, we think that your heart's going to be improving or getting worse with your disease. It might be what if testing so that you can say, I want to give drug A or drug B, and then we'll be able to predict which of those, what the outcome will be. And then that can be used to inform therapy selection or patient selection for a trial. Or it might just be providing additional insight so that we have a patient, we can see that we can do some tests to find out what are the main proteins or main factors which are determining their disease progression. And that could then go on to inform a device therapy or a new diagnostic.
When we spoke to you then, I think it was very much still on the theoretical sort of basis, but you were going from then to do initial studies in sort of hospital or clinical settings. What's happened since then? Where are we at with digital twins of people's hearts?
Yep, so we've got to a point with digital twins that they've been used in kind of early clinical studies, I would say, where the feasibility has been demonstrated, particularly in areas like ventricular tachycardias and atrial fibrillation have been demonstrated at Johns Hopkins, and we've looked at how we can guide heart failure therapies that we did at St. Thomas's Hospital. Those have been very much models of an individual patient to inform a specific decision. We've also more recently been awarded a EPSRC program grant, and that's CVDNet. And in that grant, we're working with patients who are pulmonary arterial hypertension patients, and they have implanted sensors. And that then gives us these kind of continuous measurements that we can use to update our mathematical models of the patients and then make continuous forecasts. And so that's what we're working on now. And there's a number of parts that have to come together from both the mathematics side of it, but also from the data governance side of it, and also from the patient engagement and understanding patients' awareness, their understanding of a digital twin, understanding how we can kind of communicate digital twin results to those individuals.
So it's interesting. So you've done these initial studies for specific diseases, and now you've got this big program where you're actually where you've got models of particular patients, their hearts are being updated with data through this monitoring. Richard, so what's your involvement with the sort of digital twin stuff?
So my involvement, I guess, in some sense, I'm Steve's pet statistician. So I've been working with Steve for a decade now, and so I'm not. I've learned a little bit about hearts, but it's not my expertise. So my end of things is definitely the uncertainty quantification end of things, and so it's helping Steve tackle the challenges they have in that cardiac setting.
Is that a setting you've worked in before, or?
No, it's not actually. So I've not done anything medical before. So my background was doing research, uncertainty quantification, so parameter estimation in complex models. And the application areas I'd worked in before were like climate science, geoscience, paleontology and genetics. So kind of a diverse range of fields, but never medicine before. But mathematically, the ideas are the same and the techniques are the same, just a new setting for me.
Are they always similar models, or are they?
They have some similarities. So the similarity between what we're doing, say, with hearts and with climate is they are big, expensive, deterministic models that are based on partial differential equations. Okay, so in that sense, they're quite similar in how they behave and the kind of methods that are going to work.
What do you hope would be the benefit of having something like the digital heart? What would the impact be either on advances in medicine more generally or in individual treatment of patients?
So there's multiple potential benefits. The most ambitious in some sense is to guide treatment. So we can collect data from patients very intensively by inserting cathodes inside their heart and measuring electrical activity or pressures. But we can only do that for short periods of time. So hopefully what the twins will allow us to do, digital twins, is to be able to infer what's happening even when they're not in the hospital. And if we have that information, then we can start to ask what if questions, or if the surgeon does this, or if we give them this medicine, what will the effect be on them? But there's also a monitoring aspect. So the big new project that Steve's leading, that I'm involved in, is looking at pulmonary hypertension patients. And this is a group of very sick patients. And there's only 5 centres around the UK that treat these patients. And the way the NHS typically works is that you have an appointment set up every 6 months, and they travel in, and sometimes they didn't need to travel in. Or sometimes maybe they needed to go in, but the appointment's sometime in the future. So hopefully we can use these twins that are tracking their state, the state of their illness, their current health, and use that information to say, okay, we don't need to see you this month, come in 3 months instead. or to be able to phone them and say, I think you need to come in, we need to speak to you, and see what's going on and maybe change your treatment because what we're doing at the moment isn't working. So I think there are two main uses.
In that second example, would those digital twins, I mean, that's such an interesting idea. Would those digital twins of their hearts be getting updated data from the patient remotely or something? Is that the idea?
That is the idea, yeah. So in this new project, part of the project is implanting pressure sensors directly in to the pulmonary artery. So we'll have not quite real time, but at least daily measures of what is happening in terms of the pressure buildup in the heart, which is the key kind of symptom in pulmonary hypertension. Obviously, that is a thing that we can only afford to do for a small number of patients. And so part of the project is trying to, first of all, what can we say when we do have that data? But then link that data to more easily collectible things, perhaps from smartwatches or other wearable devices. And if we can make that link between this kind of messier, noisier data to the more precise data, and then link that precise data to outcomes, then we might have a useful tool that would work at scale for the entire population of patients.
What were the impacts you got from that initial Fickle Heart program at the INI?
I mean, so for us, the Fickle Heart program was, I was great at the INI because it brought together a bunch of people who were not necessarily in the healthcare space. So we had people who attended the meeting who came from the nonlinear dynamic space and from infrastructure space, and they were able to come and say, share some of the lessons that they'd learned from things like wind farms. So in wind farms, you might have a mechanical failure in one of your turbines, and you don't want to have a lot of these, and you don't expect to have a lot of these, but when you do have one, you want to learn from that failure and apply it to all the other wind turbines in your farm. And that same idea, you can see how you can use that in patients. So we have a patient and they might have an adverse event under a stress condition or to a therapy or for whatever as their disease progresses. And then we want to share that information from that person with all the other patients who represent with similar kind of backgrounds. And so how can we kind of optimize that learning between the different individuals where we have digital twins of them? So for me, that was a great opportunity to kind of bring in people from different areas into the project.
It's so interesting, the idea that, because I mean, ethically, I can see why you'd want to share that learning from one patient or one problem with a wind turbine across everything, but that you sort of mathematically have to understand how to deal with that information as well. And I was interested as well, how did that program impact what's happened since, and maybe the RCL program? Is there any interplay between those?
Yeah, absolutely. So when we wrote the RCL program proposal, because we have to submit an outline proposal of what we're going to do, I think it was very influenced by my experience with Steve on what problems matter. Mathematicians will always find interesting things to work on, and statisticians will always find interesting technical problems. And it's the challenge for me, at least, is making sure those problems are relevant to the real world in some way. What's going to matter to some end user. And so I think that the Fickle Heart program really opened my eyes, and lots of other mathematicians who came to what are the challenges in this setting where we have very big, expensive models, very sparse, possibly noisy data, and very hard kind of decision problems. How do statistics need to develop to be useful in that setting? And I think more directly from the Fickle Heart program, one of the big outcomes was Steve's program grant. So that's almost £10 million over 5 years to develop exemplar digital twins for this pulmonary hypertension patient group. And I think everyone who is part of that program was at the Fickle Heart workshop at the INI. So I think the seeds of it started there, even if Steve had been thinking about it for longer than that.
Oh, that's really interesting. So the RCL program is about representing, calibrating, and leveraging uncertainty. So how does that relate then to these models of digital twins, in particular of the heart that you've been working on with Steve?
Yeah. So to take the three kind of key strands in turn. So representing uncertainty. Statisticians are typically very good at representing uncertainty when it's about a number, a continuous number. So what's the temperature going to be in Cambridge tomorrow? We know how to model uncertainty and evaluate it and so on. It becomes harder when the objects we're talking about live in a more complex space. So, for example, if you're predicting the shape of proteins, or in our case, we're predicting processes that are to do with the heart, and the heart has a shape. So, for example, arrhythmias are to do with the electrical waves spreading on the surface of the heart. So our data live on this two-dimensional, non-Euclidean, so non-kind of uniform surface. And thus, we need to develop new mathematics to figure out how to represent uncertainties in those more complex spaces.
And what are you drawing on work already done in other fields to do those representations? What sort of ideas are you using for that?
So the pure mathematicians have done lots of work in various fields on non-Euclidean spaces, and so actually we're trying to borrow the theory that exists in that more abstract space and see if we can extend the kind of methods we have, which are Gaussian processes or sometimes called kernel methods, to work when the base space we're working with is one of those more complex objects. So absolutely, there is a whole branch of mathematics that deals with these things, and it's kind of joining that together with machine learning to make progress. So we're not reinventing hard abstract mathematics here, we're borrowing from those fields.
So one aspect of the program is this idea of how you represent uncertainty when the thing you're dealing with is a complex object and there's perhaps lots of complicated data across that object. Calibrating to do with...
So calibrating uncertainty has several meanings, but one, the most common interpretation is how do we assess a distribution? So you're familiar with weather forecasters. Maybe one weather forecaster says tomorrow it'll rain with probability 40%. Another one says 30%, and then it does or doesn't rain. And those prediction processes repeat over a year. And how do we at the end say who was a good forecaster and who was a poor forecaster? Mm-hmm. And so calibration is a way of measuring the skill of forecasts. In our setting, it often means something slightly different. So it means how can we adjust the forecasts to achieve calibration, which is a particular kind of property. So particularly in these big complex models, we want to adjust the input parameters to those models so that we get forecasts that have properties we like. And we call that calibration of computer models. And so it's how we do that efficiently is the challenge. When we have these models of the heart, for example, we might start by doing an MRI scan to learn the shape of the heart. And then we build a model that models processes on that shape. But the processes all have these three parameters. So, for example, how fast does the tissue conduct electrical waves? And it might conduct electrical waves differently in what we call a fiber direction, in certain directions, to other directions, which is how the cells line up. So that's two parameters that we have that we can turn to try and get the models to align with the data we have. So that's kind of what we're doing there. We're twisting those knobs, turning those knobs to try and find a good setting of our simulator so that it replicates the data we're seeing.
And then the final part of that name of the program is leveraging uncertainty. So what do you do with that?
So I guess that's where it gets more technical. and more kind of in mainstream computational statistics. So briefly, it's how when we have a model that makes predictions that is uncertain, or once we've got a quantification of uncertainty around it, how can we use those models with that uncertainty to do things better? So often, well, primarily for us, that is how we speed up existing kind of methodological things we do.
And that's because there's costs associated with these experiments to learn those.
In our setting, in the cardiac setting, it might be, what data do we collect from the patient next? So again, back to the arrhythmia setting, the patients who have arrhythmias often undergo some sort of electrical pacing, where a surgeon will take over the pacing of the heart, send certain signals, and collect the data. And so that is a very intense process. It's only, it's got to all take place in an hour's surgery. So you have a limited amount of data you can collect, and it's kind of what is most valuable. But there's also the sense with the computer models. The computer models are expensive to run. So I think Steve's group spends about £10,000 to create a model for one patient at the moment. That's all a computer simulation. So we want to be able to pick what are the most valuable computer simulations to do next to minimize that cost and minimize the time required.
And the RCL program's been running since May, and it's wrapping up soon. And you were saying today is actually your last day. How have you found the opportunity of having this longer program and having those groups of people together? Is there something in particular that you found particularly useful, or that you think you'll all take forward from this program?
I mean, it's been fantastic for me. I've learned a lot of new maths. I've learned a lot about fields I knew nothing about before, and made friends and connections and future collaborators across a kind of diverse area. I think the thing that probably most people would say most useful is having people from very distinct areas in statistics and machine learning and application domains. People who don't necessarily go to the same conferences, don't write for the same journals, don't read each other's work normally. And so having that time to spend just hanging out, hearing each other's talks, discussing, and so on, it's super valuable to get that cross-fertilization of ideas that we don't normally get a chance to do at these kind of venues.
So it's the generosity of time, but also it's the fact that it's brought together people who wouldn't always be attending the same things.
Absolutely. So for example, there's lots of people, so I work in Gaussian processes, and there's a parallel kind of community or world that works on essentially the same ideas, but calls it kernel methods. And we never talk to each other normally, because they have different traditions and different emphases in style and so on. And so the kernel methods people tend to be much more mathematical, technical, proving theorems and proofs, and the Gaussian process side tends to be more machine learning-y and kind of embedded in applications. And so putting those two groups together has been fascinating for understanding what we can kind of both learn and gain from each other. And
just that idea that bringing together people from really different areas. Richard was saying that, there's people who are working in actually quite similar problems, but they just are in different settings, so they don't talk to each other. It's interesting, the power of actually bringing people physically together in a place can give you that.
Yeah, I mean, I think that the challenge that we've seen, particularly from the biological side, is that you have people like myself and like other people in the field who have either come from an engineering, and so they've done a lot of finite element numerical methods, or they might have come from a systems biology and they've had to learn some ordinary differential equations and how to solve those. Then they've had to learn enough biology to be able to kind of link those two together. And then they've had maybe some clinical information, then maybe some image processing. And you end up with the number of areas that you need to have becomes quite challenging. And so you see a lot of people in the mathematical biology community, I would say, focused on not necessarily adopting some of these AI methods which have been used in other kind of engineering methods, engineering domains. And that kind of this interface that we're having is really allowing us to take some of the emulation methods, some of the calibration methods, which have come from petroleum engineering or aerospace engineering, and apply those into biology, where people already feel like they have to know too many things.
Yeah, I mean, that's the thing. This fascinating research happens at the boundaries of all these fields, but then how you actually find a way to let all of those people talk to each other at the right level is a real challenge.
It is. I think it requires a comfortableness with admitting that you don't know things, and a comfortableness with hoping you know something and opening your mouth to articulate your idea, and then having a kind of a constructive space to discuss those ideas. And it really requires everyone to want to do that. And so you need to have mathematicians who are going to accept that the problem might not be defined in exactly the equation that they want to see. And it requires the biologist to at least attempt to get their problem into the mathematical form that the mathematician would like to see. And that can be a challenging dialogue, but both sides need to want that to happen.
I think for mathematicians, it's often the need to compromise. So mathematicians are very good at working within a particular framework where you assume certain things are true, and working outwards to some sort of conclusion. Whereas I think, particularly in medical fields, we don't necessarily know the true setting, and there's more uncertainty, and we might have to compromise in places in our kind of analysis to make progress in other directions. And I think that can be uncomfortable sometimes for mathematicians.
So it's the fact that you're bringing together, not just bringing together the people, but you're bringing them together in a space that makes it clear that this is what it's for. It's for those cross-disciplinary, no question is stupid. You're bringing all points are going to be bringing good content to it.
For me, the Isaac Newton Institute is just a fantastic space. And I think the infrastructure and support and the kind of the processes they have to enable people to come together is excellent and not to be underestimated. That I think the administrative staff there do just a fantastic job, and I would if there's that's an important part of it as well, because everyone's busy. Going somewhere for a time, it's a commitment. But you turn up and it all works really wonderfully. So I think that they really have done a great job there, and it's a great asset.
So that was Steven Niederer telling us about how important our lovely colleagues at the Newton Institute are in providing a really constructive space for researchers to come together to take mathematical science research forward.
So yes, thanks to Steven and to Richard Wilkinson for talking to us for this podcast. We'll put links to all the things we've mentioned here in the show notes. But that's it for today's podcast. If you've enjoyed listening, please recommend us to a friend or rate and review it wherever you're listening. Thanks for listening, and bye for now.
Bye.